Now we're going to move on and talk about transmutation and nuclear energy, describing the synthesis of the nuclides, the ones that do not occur naturally, and explaining nuclear fission and fusion processes and how these concepts of critical mass and nuclear chain reactions take place. Okay, so with this, first of all, what happens in a fission reaction is that you have a high energy neutron that impacts with the U-235, a radioactive uranium atom, and it breaks into, it forms an unstable nucleus, which then erupts and forms both a krypton and a barium plus 3 neutrons. Okay? The fact that you get 3 neutrons out of this means that if there is additional uranium there, it's going to have the opportunity to have 3 of these impacting those next ones. So this very large amount of energy that you get is just going to be amplified again and again and again if you have what is called critical mass. In other words, enough mass present so that these right here just keep on going and keep on going until all of it is released. So the nuclear fission of U-235 produces a range of fission products. Okay, and it shows that you can have, it can go to U-236-92, which will form strontium and xenon plus 2 of these. It can form bromine and lanthanum plus 3. It can form rubidium and cesium and 3, tellurium and zirconium and 2, barium and krypton and 3. So in every single one of these cases, it's going to result in having more of these neutrons than the initial neutrons that started off the whole process. And so right here, what you can see is you get a range of different ones coming from these two. You'll get ones that are a little bit, you get 144 here, 146 here, 137, 137, 141. The lower one is 90, 87, 96, 97, 92. So you get ones that are around this range, you get ones that are around this range right here for this each one of these. So the fission of a large nucleus, such as U-235, produces 2 or 3 neutrons, each of which is capable of causing fission in another nucleus by the reaction shown. If this process continues, a nuclear chain reaction occurs. In subcritical mass, the fissile material, in other words, those that can cause fission, are too small and allows too many neutrons to escape. Okay? So a chain reaction doesn't occur. In critical mass, a large number of neutrons stay inside there and induce fission or create a chain reaction. The nuclear fission bomb that destroyed Hiroshima in August 6, 1945, consisted of 2 subcritical masses of U-235, where conventional explosions were used to fire one at the other one, creating a critical mass for the nuclear explosion. The plutonium bomb that destroyed Nagasaki on August 12th consisted of a hollow sphere of plutonium that was rapidly compressed by conventional explosives. So the explosives were around this, slamming it, so it had to detonate all at the same time to compress them down to form critical mass here. Here you had them separated by a distance, and this right here slammed it into this so that it rapidly achieved critical mass here. 2 different ways of approaching this same destructive effect. Here you have the ability to harness that power to do it under a controlled fashion so that you generate heat and have steam generators for that. You've got walls so that it's all contained, and the steam that's heated powers turbines that are outside of the system. And you've got essentially your core here, and what you have is you've got rods that go into that core to essentially absorb neutrons and essentially slow that process down so that you never reach critical mass. And that's the fail-safe system for these, so that in the closed system, when a shutdown system, it shuts down safely to push those rods into the core, and therefore it cannot achieve critical mass. Here's the nuclear core right here showing the fuel, and then these control rods that are here in this center. And they have the different containment levels around them, and there's 2 levels of containment, and then another third larger one around the whole core, and before anything goes out to the outside. With proper engineering, this is a very safe technology. This was a 3 Mile Island. Again, there was 2 different reactors here. One was unaffected by the other one, and it continues to generate power to this day. And the accident resulted in no release outside into the environment. The news media of the day kept photographing these clouds right here. This is essentially steam coming from the steam generators. That is not any nuclear waste associated with that. And this is the International Thermonuclear Experimental Reactor. And this is where they're trying to get a fusion reaction going. Okay? So what they're hoping will happen there is that fusion, which is powered by utilizes lower molecular materials, would be a lot safer and produce a lot more energy than the nuclear reaction. Okay, and it uses these lasers that pump energy into that, and they're lasting only a few billionths of a second right now. Okay, so it's not self-sustaining at this time, and it's only a laboratory way of doing it. We should have had this by now had they continued working with the nuclear program back in the 70s and 80s, but all of that shut down, unfortunately, in the mid-70s in this country. Use of radioisotopes. Okay, this is there are thallium-201, for example, is administered to a patient, and then what they do is they have all these monitors so they can visualize the heart function as that person works out on a treadmill. Another one is technetium-99, and that's is used to separate technetium-99 from molybdenum-99, and this what can happen here is you can scan this in the person's neck with Graves' disease, and the high concentrations of this shows where the problem occurs, and so that when they have to do their surgery, they know exactly what to do. And this is a Cobalt-60 machine, just a mock-up of it, where they essentially target they have radioactive cobalt in there. Gamma rays essentially focus on the tumor region, so you can either treat the tumor that way, or you can do other, sometimes you can also utilize it to do brain scans as well. Cobalt undergoes a series of radioactive decay, and it shows the energy level for each one of these different ones, right? And how much of it goes in each one. Other uses of radiation are examination of things at the airport, including bodies now, and the preservation of fruit. Here's an ionization chamber, a small amount of radioactivity there, and what happens there is you are the americium-241 emits an alpha particle that ionizes the air, creating a small electric current. During a fire, the smoke particles impede the flow of the ions, reducing the current thus triggering the alarm. Okay, and so if also that means you also have to change the battery from time to time. Otherwise, you're going to have very annoying little beeps. Biological effects. Okay, let's talk about that. Anytime you have radiation, you're going to have some DNA damage. Okay, and that can be helpful in terms of if you are trying to destroy a cancer cell, or it can create a cancer cell and then have tumors resulting from that. If this damage is not properly repaired, that's when the tumors result. And so you can see what are the non-ionizing and then ionizing different ones. So I have increase in energy this way, increase in frequency, increase in wavelength this way. So lower frequency, lower energy electromagnetic radiation is non-ionizing. Higher frequency, high energy electromagnetic radiation is ionizing. So these are the ones you have to worry about. The gamma rays and the X-rays. Okay, these are the ones right here that are used medically, and while it does damage the DNA to some extent, it also can be very, very useful. Just have to do it in control. So the direct effect is of this. With the water and radiation, this is an indirect effect, right? So ionization radiation can directly damage a biomolecule by ionizing or breaking its bonds, or create hydronium ion here, which reacts with water to form the hydroxyl radical, which in turn reacts with the biomolecule, causing damage indirectly. Okay? So I don't know. Both of these are direct damage. This right here just involves another couple of chemical reactions in addition. Now, you can stop radiation quite easily. A single sheet of paper will stop an alpha particle. A thin sheet of metal, aluminum, about a quarter of an inch thick, will stop a beta particle. A neutron can be stopped by a glass of water, a few inches thick of water. Gamma radiation, it takes several inches of concrete, or I think 6 inches or 6 to 12 inches of concrete, or 2 inches of lead to stop a gamma ray. So the penetrating power is alpha, can stop by almost anything. Beta is stopped by things that are just a little tougher. Neutrons takes a little bit more density than gamma, as it really takes quite a bit to stop it. Radon seeps into your house from rocks containing uranium-238. This is a radon emitter, and it gets in through the cracks and foundations, and so you do check your house for different presence of radon. Devices, Geiger counter and scintillators and dosimeters are used to measure radiation, and depending upon which ones you have there, determines your dosage. The rate of decay is measured in becquerels or curies, and the absorbed dose is measured in grays, rads, or rem. Okay, so that's the absorbed dose right there. Okay, so this is for radioactive decay itself. This is how much a person and that's why it's placed on your body. Is if it's this right here is absorbing it, your body is absorbing it as well. And this is the total annual radiation exposure for a person in the United States is about 620 millirems. Okay, and this just goes to show you what the different things that you can expect, what sources of those different ones. Just walking down the street in New York City is going to give you some. Okay, this is your dose limit right here. Okay, and this is the other ones are just your radiation doses. Okay, so anyway, that is the information on this particular chapter, and we'll stop there and begin the next video with the information on the medicinal chemistry.